Hello students, in this video we're going to construct the slope field, or sometimes it's known as a direction field, of the following ordinary differential equation. Alright, so first off, let's construct a sign chart, or sometimes people call this a number line. What I'm going to do here is I'm going to analyze where is dy dt positive and negative. So first thing I do is I look for the intercepts here, and y equals 3 and y equals 0, and I place them on the line. You'll notice that I made this line vertical. There's a reason for that. We typically do that in ODEs. And the reason is we call that a phase portrait, and when we actually draw the slope field, you'll see this will match up real nicely with our slope field. So anyways, here's our phase portrait, and you notice that dy dt, when y is larger than 3, this will be negative, but this part will be positive. So negative times positive is negative. Between 0 and 3, this will be positive, and this term will be positive, so the positive product of two positive terms will be positive. And then, of course, when y is less than 0, that'll be negative, but this will be positive, so negative times positive is negative. So that means that dy dt is less than 0 when y is greater than 3. It's greater than 0 when y is between 0 and 3. And it is less than 0 when y is less than 0. So what we see here is that the function y is actually increasing, and between 0 and 3, decreasing when you're greater than 3, and decreasing when you're less than 0. And it is 0 at 0 and 3, and we call those equilibrium solutions. That's where dy dt is 0 in both cases. And then, as I said, y is decreasing above 3, increasing between 0 and 3, and decreasing when y is less than 0. And let's see how that matches up with our slope field. So first I'll just get a rough sketch. I'll put in the equilibrium solutions, and you notice that it seems that y is being attracted to 3, so we call that an attractor. And if I just put in my slopes, they're all going to be they're going to be slanted this way because y is decreasing. And then between 0 and 3, since y is increasing, all my slopes will look in this direction. And so this is a very rough sketch. And then less than 0, the slopes will go in this direction down to the right because y is decreasing, and dy dt is less than 0. So this does not capture the nuance of the slope field, but it gives us a general sense of what the solution is going to look like. And here is the actual slope field. So you see that the solutions are asymptoting towards the equilibrium solution, this blue line here, which is y equals 3, and they are repelling from y equals 0. And you notice there's some curvature to the slope field that was not captured in this analysis nor in the phase portrait. And I'm not going to show the details in this video, but I will point out that if you were to take the second derivative of this term here, you would end up with, if you worked it out, you'd end up with this term here. So you'd have a product of these three terms, y times 2y minus 3 times y minus 3, and if you did the sign analysis on this, you'd have concave down less than 0, concave up between 0 and 1.5, concave down between 1.5 and 3, and concave up when y is greater than 3. Now look at that. When y is greater than 3, we're concave up. So that's where that curvature comes in. When you're above 1.5, which I drew in here, this is our point of inflection, and this is, some people call this the point of maximum acceleration in a population growth, if we think of this as a population model. And you're concave up when you're below 1.5, but concave down when you're above 1.5. And then when you're less than 0, you are concave down. We'll do this analysis in another video when we analyze the logistic equation, which is what this equation is. But for now, the takeaway in this video is just can you draw a phase portrait, tell where the equilibrium solutions are, tell where the functions increasing and decreasing, can you draw this rough sketch, and can you tell where the attractors and repellers are? Those would, I think, be good expectations to meet. in doing this analysis. And then once you saw the slope field after we plotted it maybe with some technology, you'd be able to recognize and match up this differential equation with its respective slope field. Any further analysis we'll leave for a future video. All right, good luck.